All right. Hi, guys. Welcome to Manufacturing Month. Today we have JSR Micro with us, and they're going to do a presentation. So just a few housekeeping things before we get started. So we have great questions at the bottom left corner. And so these are really great questions to ask the presenter because I know you get a lot of information. You're like, what do I even ask about? Those are really great questions to get you started. I also wanted to let you know we have a check-in form and we would really like it if you guys submitted that. It just kind of helps your counselors know where you're at and know that you're safely in the meeting and not maybe in class, and just to know where you are. And then I also wanted to let you know, in case you haven't heard, we have a Manufacturing Month scholarship where we are going to be offering five 500 scholarships or five $500 scholarships to high school students, five going to high school teachers, and then two going to middle school teachers. And so these scholarships are primarily if you enjoy a career event, you can talk about that. You can make a poster, you can make a video, you can have an essay, whatever, calls to you. So like within this scholarship, we want to know what interested you. How do you imagine manufacturing for you in the future? And, just how does STEM play in your life? And so with this $500, we also want to know what you're going to use the money for, whether you're building a car, you're fixing up your car, or whether you want a sewing machine. So there's a couple different options that you guys can have. It's pretty much unlimited options. And then I also wanted to let you guys, there we go. So go ahead and stay fully present during the presentation. Try to limit your phone use unless you're using the QR codes. And, listen, because these are great jobs. I've been with these, I've been listening to all these different presenters, and it almost makes me want to switch careers. So, and then go ahead and submit your evaluation at the end. So this is how you're going to get the career credit for attending this presentation. So I think that is about it. So I'll go ahead and stop sharing. Then Brian, you can go ahead and get started.
Okay, thank you very much. Let me share my screen as well. Give me 1 second. So let me know if you guys can see the presentation.
We can.
Okay, great. Well, welcome everybody. My name is Brian Osborne. I'm the plant manager at our JSR facility in Hillsboro, Oregon. So welcome to everybody. And of course, this is STC Manufacturing Month, and we're JSR Micro, but of course, who the heck are you guys, right? So I want to give you guys a brief overview of JSR, myself, and my role at the company, and some of my backgrounds, the technical issues that we're trying to address, and then of course we'll wrap up with like Q&A at the end, and give you some verbal explanation and description of the types of people that we employ at JSR. And so I'll dig in. So again, my name is Brian. I've been with JSR for over 12 years now, and with this is JSR is a material supplier for the semiconductor manufacturing domain, we can say. So our customers are companies like Intel or TSMC or Samsung or Micron. So some companies you may have heard of that make semiconductor chips, microchips on wafer fabrication devices. But we're a chemical material company. So at our facility in Hillsboro, we do chemical manufacturing, and it lines up well with my career. I'm a chemist by nature and by training. I went to high school in Austin, Texas. I did my undergrad in Austin, Texas at UT, so Longhorn. I did that in chemistry, so I got a bachelor's in chemistry. Then I moved on and did a master's degree in chemistry at Georgia Tech, and so that was the next part of my career. Then came back for graduate school at the University of Texas again. I just couldn't stay away, and finished up my PhD in synthetic organic chemistry, working on polymer chemistry for semiconductors. So I was a career student, and then, went to a company called Advanced Micro Devices that some of you who do PC gaming or build your own PCs may know of them. They're a competitor to Intel. They make CPUs. They also make GPUs for video cards. And so I worked there for about 6 years on the logic side, and then also moved into the company called Spansion that did flash memory. So that's different from CPUs. That's just the memory chips that you get in like your USB drives, for example. Then after that, so after working on the semiconductor manufacturing side, then moved to JSR. And I've been with JSR, like I mentioned, for about 12 years. And I've had a good career at JSR. Honestly, it's been a really great place to work, and it's been really good for my career. One of the things that I learned is especially coming from AMD back in those days when they were a really tough underdog to Intel, but also struggling financially, different from how things are today, is that when I went to JSR, I really did understand that in your career, you have to, if you want to get ahead, if you want to take control of your own destiny, so to speak, it's always good to take advantage of any opportunities. So instead of just doing my own regular job and just kind of the 9 to 5, I would always look for extra work to do or other groups to work with and help, a little bit here or there, not like two or three times the work, but other ways that I could contribute and help, even in non-technical ways, honestly, just even by tidying up or cleaning or helping to organize meetings or start the go-to meeting or the Skype meeting or something like that when nobody else was around. So all like the little things, and then working with other departments, and then eventually applying for positions where it was on the management side. And so a lot of that background of being helpful and being social as well as technical was very helpful in order for me to move from where I started in JSR, which was on the research and development side. So definitely like the traditional chemistry nerd and working in like the lab and, mixing some formulations together and chemicals, to then moving to outside of R&D. So out of the comfort zone into quality control, where they take things very seriously and things are very analytical and things are very statistical and precise and accurate and all those good things that you have to do in QC. So I learned a lot of discipline moving into that direction. Then eventually grew from that into also helping to manage an engineering group, where that's scaling up things from like really small stuff that you do in the hood to stuff that you do in a manufacturing plant like we have here in Hillsboro now at our brand new facility. And then took the step after that to plant management, because after working with R&D and then quality control and then engineering, kind of had like a bit of a package of experience under my belt, and was able to get my way into the plant management role. So that's a little bit about me. So we run a chemical manufacturing plant here in Hillsboro that I'll tell you guys more about in the coming slides. And it's really chemical engineering, right? So there's a lot of chemical operations, there's a lot of material handling, there's a lot of operational logistics with tankers and isotainers, because it's a really high volume business. So we deal in thousands and thousands of gallons of chemicals here in order to make products for our customers, who you can guess who one of our customers might be. They're just 5 minutes south of us here in Hillsboro. And so that's the challenge that we have in front of us today. So just a little bit of background from me, and then I'll give you guys some more background on JSR. So let me move from slide 1 to 2. So hopefully it's moved to slide 2. If it hasn't, just pipe up and let me know.
It has not.
Oh, it has not.
It's showing your whole presentation.
Oh, okay. Thank you. Thanks for saying something.
Might
Appreciate
need to
that.
unshare and then reshare.
Let's try that. How's that?
Yes.
Okay, great. So, okay, and thanks for piping in on that. So that's very helpful. So yeah, I'm on dual monitors, and I think I would have to switch the monitors, but instead of doing that, I'll just go to this mode, which is fine. So the JSR is an international company. Originally, JSR, just like many businesses and many industries, semiconductor is no different. They like acronyms, right? So I worked at AMD, now I work at JSR, right? So TSMC, everybody has like an acronym. So JSR started basically about 60 years ago almost, and it was a post-World War II company in Japan. So the J stood for Japan. The S and the R originally stood for synthetic rubber. So after post-World War II, Japan, since they were limited to non-military type of technologies because of the war and some of the treaties that were signed after that, then JSR became a company to supply rubber to the automotive industry. So, and again, this is, back in the early 50s. So our experience and like our knowledge base throughout the decades is on polymers, right? Because for your car tires, it's rubber, but rubber is a polymer. And so we really know a lot about polymers. And but JSR has spread that little bit of chemical knowledge into a huge, pamphlet of like different business areas, right? So you can see, hopefully, since I can't do the pointer, but I have the mouse, but we're in semiconductor materials. So that's the area of business that we work on at Hillsboro at our new site. What we call packaging materials, where you take the little silicon piece of processing power or like the silicon chip, you cut it out of like the wafer and you package it into like one of these packages that goes onto like a circuit board or a motherboard. Display materials, so like the screens that you guys are looking on now on a PC or on a laptop, they're powered by LCDs, like another acronym, right? So liquid crystals for liquid crystal displays. And so we make the materials for that as well. And then things that go into like mobile devices. We're also, again, into elastomers. So that's more of like tire business where you're using rubber. There are also things that are called like thermoplastic elastomers, which it's just a different type of curing process. And it goes into things like, as you can see from the picture, like, running shoes and the like. We're also into the life science business. So that's become a bigger business for us now. So we have the semiconductor side, we have like the rubber polymer side, and then we also have life sciences. So we're in biotech as well. There are emulsions, there are plastics, and then of course, as is the rage these days with 3D printing, we do make precursor materials for 3D printing, and specifically ones that like have a really high carbon content. So JSR materials are in a lot of different places, a lot of different areas. For the manufacturing site we have here in Hillsboro, what we're looking for are people who can help us in the semiconductor material space. So specifically, this is where we make product for our customers, is in semiconductors. Okay. Move to slide 3. Again, just pipe in if you can't see it. But again, just to kind of show you that JSR, we're not just in Hillsboro, we have locations all around the world. And I think it should come as no surprise that a company that used to stand for Japan Synthetic Rubber has a lot of facilities in Japan. So you can see the islands of Japan here on the right side of the slide, and that's where our headquarters are at. So the corporate headquarters are in Tokyo. And then there's a city called Yokkaichi, about 2 or 3 hours south of Tokyo, where the original R&D facility started and the original high volume manufacturing factories for our business started. But we're throughout Asia as well. There's Korea, there's China, Taiwan, and Singapore. And this has nothing to do with all the semiconductor companies that are located in those companies. Sorry, bad joke. But of course, it's very much directly correlated to where the semiconductor companies are. So there are semiconductor manufacturers in Singapore. Taiwan has TSMC. Korea has Samsung, of course, right? And China, they have a lot of burgeoning companies in the semiconductor space too. Then we have a facility in Belgium, in Europe as well, because there are semiconductor companies that are based there as well. So your Global Foundries is headquartered in Malta, Germany, and then you have ST Micro in France, for example, Infineon, a whole bunch of other semiconductor manufacturers. So we have a manufacturing site in Belgium as well, in addition to Japan. And then we do have our facility here in Oregon. So this is one shot of it, of our factory in Oregon. And this is where we do advanced cleans. So that's the topic that I'll be sharing with you today. But we also have our factory in Sunnyvale, California, that works on photoresist. So we'll go into some of the detail on what these materials mean. But long story short, we have facilities, across the globe, and smaller offices that aren't included in the map as well. So we really are a global organization. And our factory here in Hillsboro is just barely a year old, so we're also expanding. So, okay. So yeah, what are we doing here? Why build these factories? Why do all this R&D? So this is one snapshot of Moore's Law. So likely some people on the call may have heard or have learned about Gordon Moore, who was an Intel engineer and didn't really come across, it's not a law, like it's not a lawyer type of law or any legalese like that, but it was basically an observation that a lot of engineers and Gordon Moore in particular published a paper on the observation that the density or the number of transistors that are on an integrated circuit are increasing at a rate that's pretty linear, right? Like you can kind of imagine with your eye, almost a straight line kind of going through this progression through time, right, on the x-axis. And then here is the calculations per second, and it's divided by cost as well to normalize by cost. And this is essentially a roadmap of transistor size and transistor density. So transistors started over 100 years ago, but they were mechanical in nature, and they turned into small relays. There's the old school movie vacuum tube where you see the tubes heating up and doing their thing for old transistor radios. Then they actually made digital transistors and then put them into integrated circuits. So there's a whole bunch of transistors like on the same board or on the same circuit. And this has really taken off, and it's really stayed true to almost this linear progression. And what's happening is that over time, as you go through year after year after year, the calculation power continues to increase. Like it doesn't stop. It's not like, oh, we can't do any more calculations. This is the fastest we can calculate. That's it. There really hasn't been, so far, there really hasn't been like a limit. Has it gotten more difficult? Yes. Gotten more expensive? Definitely, very much so. But this is the challenge that the semiconductor manufacturers like your Intel or TSMC or Samsung, this is the problem that they're trying to tackle. They're trying to keep up with this pace, right? In order to be like number one in semiconductor field, you have to stay on this pace. If you fall behind and your competitor does not, then now you're second place or the first loser or however you want to term it. But Moore's Law is what everybody is trying to keep up with. Okay. And so just a little bit more on Moore's Law. So what's the benefit? Like what's actually happening? Like how do you do more calculations per second? Well, without getting into like the nitty-gritty of the physics and the chemistry and all that kind of stuff, it's basically because the transistors, like the calculating devices on your phone or on your laptop, they're getting smaller. Oh, sorry about that. So they're getting smaller. So you can think of a transistor as basically a switch. So it's either on or off. And how fast it can go on and off basically determines the calculation speed. And in order to make something switch on and off quicker, you make it smaller, right? Like a kind of a silly analogy or something might be like a drawbridge or something, right? So if it's a really big drawbridge, it takes a long time for this thing to open and a long time for it to close while you're sitting in traffic, right? But if it's like a little model drawbridge or something on like a train set or something, or a smaller one or something, it can go a lot quicker because it doesn't have as much weight. You don't need as much power and bigger engines and all that stuff to drive it, right? So size does matter, but here it's smaller is better because it can switch on and off faster. And basically you're just shortening the length that the transistor has to take to communicate from one side of the transistor to another. So basically the electrons, as they flow through the circuit, they have a shorter gap to go across as you make the transistor smaller. So in order to keep up with Moore's Law and keep the calculations going and going and going, you make everything smaller. So sounds easy, very difficult and very costly. And it takes a lot of material design, a lot of physics, a lot of engineering. So as you get smaller and smaller, then the operating speed increases. You can make things more complex, right? Like the phones that we have in our pockets now are ridiculous. They're not just calculators. I mean, they're full computers. And also what's of a benefit to companies like Intel is that they can get more devices on one wafer. So that's good for them, right? Would you rather like waste one wafer for one device or get like 300 on one wafer? It's pretty obvious. Like you would like to get as many devices from one wafer as possible. So making everything smaller and shrinking it down helps that. And what Gordon Moore observed was, basically every 2 years, maybe 18 months to 24 months, is that the number of transistors for a given area that you're looking at, it's increasing, it's doubling like every 18 to 24 months, which is kind of crazy when you think about it. It's tough to keep that kind of geometric progression. And also you can see that the wafer size increases too. So back in the old days, 20 or 30 years ago, they used to have really small wafers, like 4-inch wafers, 2-inch wafers, and now they have 12-inch wafers. And also the cost goes down. So again, if you think about, the cost for somebody like Intel, if they only had one CPU or one chip that came out of a wafer, that's going to be more expensive than if they got 200 or 300 chips out of that same wafer, right? Because they only had to buy one wafer, right? But if you have to buy 300 to get 300 devices or 300 chips, then that's going to be more cost, right? So it's a business, so everybody is concerned about cost. So as the wafer size increases and the price per device decreases, the counterpart is, and that's where JSR comes in too, is that there's a lot of cost that does increase. So it's more expensive to manufacture. It's more expensive to do the R&D because this isn't just regular materials or chemicals you can get off the shelf, right? So you really have to get into the nitty-gritty of super specialized and super pure materials. And of course, your testing costs increase as well. So in order to make sure the chip is calculating at the correct speed, doing what you want to do, and it's doing it so much faster, and there's so many more of them, right? Because now you have transistors all over the chip and all over the wafer. It's more to test, and it's more difficult to test. So long story short, it's good to keep up with the Moore's Law curve, but it's not easy. It's very difficult. And that's what we as JSR can help our customers like the Intels and Samsungs with our manufacturing. Okay. And so again, just more of the, not more of, but a little bit more of an analogy to show where we've come in just, like half of a century. So on the left-hand side, you can see like in the 50s, this is like one of the original computation devices. They were closet size or room size, ENIAC, and some of those earlier computation devices where they filled entire rooms. And so here you're probably looking at maybe a couple hundred transistors or something like that. So 50 to 150. And the cost was not cheap back then, even adjusted for like, inflation and today's dollars, because the switches, which were, the original transistors at those times, like vacuum tubes and everything, the gap between one side of the transistor or one side of the vacuum tube and another was on the order of centimeters. So very intuitive to work with because you can see it with your eyes, right? You can see these transistors, you can work with them by hand, but not as fast, right? Like in 1 second, it could only, quote unquote, do about 5,000 operations a second, which is much faster than I could ever do it, and probably most people on the call too, but still for a computation device that's not limited in the same way that humans are, still pretty slow. And then if you just look 60 years from now, so this is still like 10 years ago, but we've had exponential, like, billion level increases in functionality while driving the cost down, right? So for older iPhones, this is probably like a 4 or 5 or something, I think from Apple's lineup, the cost has decreased enormously. The size has gone down from, you're not even talking about centimeters or millimeters or micrometers or microns, you're in the nanometer regime. So the size of these switches or transistors has gotten to the point where you can't see it with the naked eye, you can't see it with a regular optical microscope, you have to use some really advanced techniques to see these switches and transistors, but look at how many more operations per second you can do. It's crazy, right? And again, this is following Moore's Law, using materials from like JSR, for example, to our customers to enable this kind of change. But this is also the problem that we have to keep up with. Okay. And a little bit more because the analogies are always fun. So, like how much progress has there been? Well, I would say that other industries like automotive, as you're seeing on this slide, aerospace, like with airliners and jet planes, follow a very similar curve like Moore's Law. They have the same kind of progress, but eventually they do kind of get to a stopping point, right? Like cars can't go much faster than 300 or 400 miles an hour or something if you're on like a Salt Lake or something, and planes can't go much faster than Mach 3 or 4 and until you get into like, real space travel. But for a good comparison for where we've come on the semiconductor side is that if you'd taken, the analogy with Rolls-Royce, because they've been around for a long time, over the similar span of time as semiconductor improvements have gone, then that cost decrease we saw where, the 1950s computation devices went from, $6 million down to a phone that's $500 or in that range. Cars would, have dropped, on the order of down to like less than $100, right? Which obviously is not true, as far as I know. And their efficiency would have increased, right? Their capability would have increased as well. And so you could take a gallon of gas and you can go around the world like 8 times, right? And your top speed would be ridiculous. But of course, none of that is true because there are physical limitations on vehicles and engines, and of course, just the physics of a car or a vehicle in like atmosphere. So there are some physical limits on what you could do. But if they could have followed the same path as semiconductor, then you would have a much cheaper, faster car that goes much further on a gallon of gas, but not yet. Okay. And so just to show a little bit about getting into the nitty gritty of like, okay, well, we talk about the chips, we talk about Moore's law, we're talking about shrinking things. How does this actually work? So it's not just fancy laser beams or something like in a James Bond movie or something like that. There is a lot of chemistry that goes on as well. So what we're showing on this slide is just a very, cartoon example of a standard process to make one layer of a pattern, because computer chips are basically just circuits, right? Circuit is just like if you take like a circuit board or a motherboard, open up like the laptop or something, or a PC, you can see like all these little lines, right? Those are all the wires that are connecting one circuit, or making a circuit between one chip and another chip, right? Because they're all on the same board together, just like inside of your phone. So when you get inside the individual chip, like, well, what's inside the chip? Well, it's just composed of like a whole bunch of different layers where they put a lot of transistors on one or a couple of layers, and then the other layers are just connecting these transistors to one another. Because if you could fabricate or make a billion transistors or a trillion transistors, but they weren't connected to each other, nothing would happen. They'd just be going on and off by themselves. They wouldn't be talking to each other. But once you connect them, now you can do calculations. You can do adding and subtracting and multiplying and more complex things. But in order to take that circuit pattern and that transistor pattern onto these silicon wafers, now they're, like I mentioned, 12 inches in size, you have to do some steps. You can't just take the silicon wafer and, do one flash thing or one kind of magic step or something, and now you have a chip. You have to do multiple layers of building, transistors on some layers, and then the wiring to connect all of them on the other layers. And it's kind of like building like a skyscraper, for example. You just go floor by floor by floor by floor. And how do you build the individual floors? That's what you're looking at on slide 8. So you have the wafer that comes in, and it's a silicon wafer. So that's the gray substrate you see at the bottom. And then you put something on it, right? You deposit something on top of the wafer. And it can be something that's conductive, it can be insulating, it could be a million different things. Then you have to put some kind of pattern, because if you just coat the wafer, now you just have a coating across the whole wafer, and that doesn't really mean anything, right? So you have to make patterns within it. So at our facility in California, JSR California, we make materials that enable this patterning. So the material that's in this kind of green color, light green color, that's the material that they make. And it's a polymer-based material in like organic solvent that they spin coat onto the wafer, and they expose it to light through like a patterned mask, and it creates this pattern through the process. So, okay, great. You deposited some things, you made a pattern. Now what? Well, now you have to actually put that pattern into the original material that you deposited, right? Because this is the target material that you wanted to pattern. The JSR California material was just there to create the pattern. Then they take it to another tool and it does what's called etching, but it's literally like kind of digging out or, physically abrading the material. And so where the patterning material in green is still there, it's protecting the blue or the blue-gray material underneath it. But where we've opened up the pattern and there is none of this green material, which is called photoresist, then the etching process can go all the way down to the bottom of the silicon wafer. And that's how you transfer the pattern into this deposited layer from step number 1. So, okay, that's great. And that's what the target that was sought. We deposited material, we put a pattern into it. But the problem is after you take off like this photoresist material that our JSR California manufacturing site makes, it can leave behind after the stripping process some debris. So this is an example, like some very microscopic, nanoscopic materials. So you need to clean it. So I think intuitively, the next step after that would be cleaning. And the cleaning process is what removes these particles and defects. And so this is the material that we make here in Hillsboro. It's a cleans material. We literally call it cleans. So once you've cleaned off this pattern and it's all cleared off and the wafer is good to go and the pattern is set, now you can do something interesting with the pattern. Like you could put like copper into that area, and copper, just as you know from wires and like your headphone wires or other wires around the house, is a conductive material, and you can use it to transmit electricity from one transistor to another. And so that's just one simple cartoonish example of what the semiconductor companies go through in order to make patterns on the wafer and to make it a functioning chip, and where JSR comes in and makes materials that enable this process. So without JSR to make these materials, they wouldn't be able to do this process. So, all right. And again, we can come back to this during the Q&A, so don't worry if you don't have to memorize it or anything like that. And then just to show like, how small can things get? It's pretty crazy. So I think appropriately during a pandemic, unfortunately, like we do have a virus going around, but for our old friend, the influenza virus, so not COVID, the individual virus or the viri themselves are on the order of about 100 nanometers in diameter. So roughly plus or minus. And you can see this is, like we talked about on the previous slide, we're making those structures, right? When we're using this photoresist material. And so here it's just kind of shortened down to just resist. But you can see like from 1990 all the way till 2010, which again is 10 years ago. So this is a little bit older material that we started out with patterns on the wafer that were on the order of like 500 nanometers or 200 nanometers. So still bigger than even like the flu virus. But then, shortly after the turn of like the millennium, then we were able to get below that, like actually shrink down to 70, 40, 20, 22. Now we're into like the teens with photoresist. You'll also notice that like the photoresist, it looks like it's kind of getting shorter and shorter, which is true because as the smaller size that you pattern you get, you can't really pattern it as tall. It'll fall over and collapse and all that kind of good stuff. But by doing different material advances at our California plant and in Japan and also in Europe, we're able to make materials that can enable the semiconductor manufacturers to make smaller and smaller and smaller patterns. And again, the reason we need to make it smaller is so the transistors are smaller, so they're faster, and so the computation speed continues to increase and keep pace with Moore's law. So this is a material that we make at our Sunnyvale facility and also in Japan and Europe. But then, of course, cleans is that one step that we talked about after doing the patterning and the etching and then the stripping of the photoresist. But it's pretty straightforward, right? Is it easy? No, very difficult, but it is straightforward. So it's basically a chemical clean. So it's not quite soap and water like we do at home or at work. It's a chemical cleaning process where you can take, typically today they do single wafer process, but you could take an entire boat or an entire set of wafers. And the old school way they used to do it was to dunk it into like a chemical bath so that it would clean off the wafers, right? So very similar to cleaning stuff in a bucket, you might imagine, or doing dishes at home in a certain instance. So they would do a chemical clean, then they would rinse it with either maybe another chemical or eventually with water, and then they would dry it out. So pretty simple cartoon. These days, we do it on a single wafer basis. So this is an old picture from the web somewhere. But instead of taking like an entire rack of wafers and doing them all at once, because the cleaning process is so delicate and the residue or the particles are getting super small, it's better, it's more efficient. Let's say for the cleaning process, it's not efficient for the number of wafers. It definitely slows things down. But to get it super, super ultra clean, you do them one at a time. So a wafer comes into the tool, it gets set on like this chuck that's in the middle of the tool, and then there's a deposition of material as the wafer spins. And so the material that's being deposited onto the wafer, that's what we make at JSR here in Hillsboro, Oregon. So cleans material for semiconductor manufacturers. Okay. And then, so how do we actually make these things? So again, it's a simple process. It's is it easy? No, definitely never easy, especially because the grade of material has to be semiconductor level. So that means the quality requirements are extraordinary. So what you're not seeing here are all the clean rooms that we have to build around these vessels and filters and the filling area to make it. But it is a pretty simple process. So for the cleans materials that we talked about on the previous slide, we have a formulation or a recipe target that we have. And different components. You could have water in there, like an acid, you could have a base, and then some organics, right? So either organic solvents or some small organic components that will do kind of what is needed on the wafer. It'll clean it, number one, yes, that's always good. But remember, when they do the deposition and they do the patterning of the material on the wafer, the customers are very specific to say, don't damage any of that. So clean it, but don't damage anything, right? We want our device to work, and we just need you to clean and then get your material off the wafer without any residue or defects left over. Again, easier said than done, but in order to do that, we come up with a formulation that has the right amount of materials and types of materials, the water, acid, base, organic, and then we blend it, right? So these raw materials will be inserted into a vessel of various size. So it could be Sunnyvale, they are on the order of like, anywhere from like, I don't know, 10 gallons all the way up to maybe like 300 or 400, 500 gallon tanks, which is pretty big compared to, what we're used to every day. Here, because they use so much of the cleans material on each wafer, we have bigger tanks. So our typical tank volume here is on the order of like 4,000, 5,000 gallons or something like that, just to make the product. And then the raw materials are fed from raw material tanks that are outside in a tank farm, and those are bigger still because you need a lot of raw materials to make your product. And so what this cartoon is trying to show here with this little crossbar member here, it's an agitator, basically like a little propeller, you can imagine, that's on this rotating shaft that's hooked up to a motor at the top of the vessel. And it's pretty simple. It's just like a mixer at home in the kitchen, right? So you put all these chemicals together. You want to make sure that they're all well mixed together. It's like a homogeneous solution. So you stir it, you mix it for a while. Then we have piping that comes from the manufacturing vessel through a set of filters, or one filter, two filters. It can be, great number of filters. And again, very much similar to what you do like with kitchen sink or something, putting a filter on there just to take out particulates or take out different materials you don't want. Same thing here. We want to filter out any particles. We're making a cleans material for our customer on the semiconductor side. They definitely want our cleans product to be clean. Makes sense. So that's why we do an extended amount of filtration, and you can see in black the piping route that goes back to the vessel. So if needed, we can have the material go through the filter with one pass, get delivered back into the vessel, and then get filtered again. So you could do like this multi-pass filtration until we get to the level of defects and particles that we want. And then eventually we have like this little valve. That's what that kind of hourglass symbol represents. And then we can fill into like a container. So it could be a little glass bottle, or like a little plastic jug, or like a 55-gallon drum, or it could be like 1,000-liter tote, which is the cartoon that's being shown on this slide. So again, after adding raw materials, mixing it all together, running it through the filtration enough times until we're satisfied with the quality, then we fill it into a particular package size and type, put some labels on it, goes to the warehouse, truck comes by, we load up the truck goes over to the customer site, and then they unload it, and then they use it. They hook up the bottle or the drum or the tote to their tools, and that do the clean process that we showed before with the single wafer approach, and they do the cleaning. And then once they consume it, then they take another container from JSR and they hook it up to the tool and they do it again. And so our goal, of course, is to make a lot of this material for the customer. The goal is to make it the same way every time. It's a little bit surprising, even like I mentioned before, when I moved from the research and development side to quality control and QC, it was one of those classic questions like, what do you think the customer wants? Do they want, for one batch to another batch of the product, do they want it to be, better every time, or like the same or worse? And you go, oh, okay, of course they don't want it worse. They definitely don't want the product that's getting worse every time you make it. But if they got something that's better, that probably sounds good. And I'm like, no, the customer actually just wants it to be exactly the same every single time. And that's because as they shrink these transistors down and they make these really, really small structures, it's super difficult. Physics and Mother Nature is working very, very tough against them to make these super small device sizes. And so they want to control variation. They want to make sure that all the stuff that they're adding to the process, so the tools or the nitrogen supply or the chemicals that they put on the wafer, like from JSR, that there's no variation. It's not getting better. It's not getting worse. It's not changing. It's the same material every time. So like, okay, now that makes some sense. But controlling it so that every single time you put raw materials into the tank and every single time you make new batches, it's exactly the same as the last one, exactly the same as you made a week ago or a month ago, 6 months ago, a year ago. That gets a little bit tougher. So that's again where the rub lies on that. So that's the production process, very simple, but it is a simple process, just a little bit more complex when you get into the details. And just to give you guys an idea, I've been mentioning like the location for JSR and our manufacturing location here in Hillsboro. And so these are just a couple of maps, just kind of getting everybody oriented, but I think it's pretty straightforward. We're out here near Hillsboro, like far western side of Hillsboro. We're just off of 26th and the Brookwood exit. So we're near like the little Hillsboro airport that's out here. And kind of zooming in, you can see a little bit of the northern part of like the Hillsboro airport, and we're just really close to Highway 26, again, just off of the Brookwood exit. And this is a snapshot of what our factory looks like from a top down, just, design look. So we have these round circles, which are those raw material tanks that go outside because it is a chemical manufacturing plant. Then they get piped inside where we do production inside, and we have a warehouse, and we have utility space and everything, and some office space. And this is the factory that we have off of Star Boulevard. So that's where you guys can find us. And then this is an aerial shot of like our new factory. So sorry for the trailers in the back over here, but we were still, just wrapping up construction. So as you can see, we're kind of in the middle of some farmland that we recently we bought with the expansion and the construction of this factory. There are some of those raw material tanks that are outside the office building, and here's our manufacturing side, a manufacturing building and warehouse that you can see in the back. So brand new. We've been in the building, just over a year, at least in like the office building, and we've been, using the production side of the factory for just under a year. So very new. Looking out across the landscape. Topgolf is really near to us. That's what all these fences are on the left-hand side. And then it's hard to see maybe on your screen, but there are a bunch of cranes, huge cranes over here. That's Intel. So just a coincidence, we happen to build very close to a semiconductor manufacturer. So, those things can happen. And I think that might be it. Yeah, so again, we've been advancing technology for over 30 years in like the semiconductor space, even though the company is, twice as old. And we're coming up with material solutions. And so we definitely need help with that. We are expanding, and we have our new factory here in Hillsboro that, we're staffing as we have moved from 5-day operations, just kind of like 9 to 5. Now we've moved into 24/5 operations. And in the future, we look to go to 24/7 as we bring the factory up and we produce more and more products for our customers. But we're keeping pace with the semiconductor companies, making new materials for cleans. And this factory is going to be the leading edge for that. And that's all I had as far as an overview. I hope I didn't take too much time and left a little bit of time for questions and answers, but that's a little bit about JSR. Myself and the team that we have here, which is composed of about 60 individuals now that range from we have technicians to chemical operators, material handlers, engineers. We cover everything from the material side to chemical operations on production to the facilities management and engineering. A lot of automation on our systems as well. So, there's a lot of systems design and engineering involved as well. And we have our sales staff and account management and administration and site management. But we are still looking to grow. So that's why we wanted to come in and give you guys a little bit of a tour and a little bit of background for JSR, and definitely would be, more than happy to answer any questions you have.
So we have some question on the chat. One of them is, what made you choose this career?
Oh, okay. Very good question. What made me choose it? So, well, I was, when I was going through college, I was one of those, like I mentioned, one of the people that builds their own PCs, and I still do, just because it's kind of fun and kind of neat to do that. And so I was always into PCs and into gaming in general, like PC gaming, a little bit on consoles too, but I like PCs because you can kind of, modify things and upgrade things and overclock things and all that. So I was that kind of a gaming nerd many years ago, and still am. Then I found out at the university that there was a research group that was doing work on chemistry that was working with semiconductors. And, I was majoring in chemistry, and I didn't know what I wanted to do with the degree yet. But then when I found out, oh, they actually manufacture chips that I'm putting into the PCs that I'm building at home, using chemistry, which is what I'm studying now. And I just really didn't think that was, something that was available to me. I thought it was mostly, people that study physics or they study engineering. And I was just, the regular old chemist. So once I found out about that and was fortunate to be like a lab assistant with this research group and start working with them and understanding, oh, you can use your chemistry degree to work in semiconductor, which I already really liked as a hobby and kind of a passion, then that's where it took off for me. I was like, yeah, this is something I want to do.
Thank you. The other question would be about the wafers. Do they get damaged easily?
That's a very good question as well. In the fact that, yeah, from a human being perspective, like for you and me, yeah, you can pick up a wafer and you can snap it with your hands, no problem. Like they're super fragile, super easy to break. If you took a box of wafers, and of course, don't ever advise doing this, and customers would definitely forbid that, is picking up a box of wafers and even just shaking them really, really, severely or even gently can definitely damage the structures on the wafer. So the wafer might be okay, it doesn't break, but the structures could be damaged. So what's happened for the most advanced manufacturers like Intel, for example, is the humans don't touch the wafers anymore. So they used to, like even when I started working at AMD, you'd pick up the wafer, a boat of wafers or a cassette of wafers or something and move it around the clean room and go to one tool and put it on the other tool and I'd do it by hand, right? Yeah, you're in a clean room suit and you got gloves on and you're not touching the wafers physically, but you're picking up the boxes of wafers and moving them from one place to another. Now that doesn't happen anymore. It's all robots, right? So they have like a train system. It picks up the wafer, it moves it to like another tool, and the tool, accepts it and opens the door. And so the humans don't interact with them at all. But yeah, long story short, very delicate. They could be damaged quite easily.
Thank you. And the other question is about your openings. How does someone apply there? And is there an HR to contact that you can share?
Oh, sure. So yes and yes. So also on the line is Abby Horrocks. So she's our site manager, office manager, and human resources director for JSR here in Oregon for both our R&D site that's in Beaverton and our manufacturing site in Hillsboro that I talked about. So after the meeting, we can send out contact information. Also, on our website, so we can give a link to that afterwards, but at jsrmicro.com, there's a link in there for careers and you can go in and click the link and it'll take you into like a portal that shows you all the current openings that we have. You'll see openings for California and some other national ones and then a whole bunch for Oregon as well.
And what is the important qualities or skills that is needed for the job?
Skills and qualities needed for the job. So I think the first one would be some technical acumen, right? You have to be curious a little bit about the technical aspects. You don't have to have a PhD. You don't have to have like a bachelor's degree for all of the positions, but it's a chemical manufacturing plant, right? So the chemicals, it's not like we're just working with water, which even water has its own dangers too, right? You could drown or all that kind of stuff too, right? But obviously chemicals are a completely different hazard level. And some of the chemicals we use are pretty innocuous. Some of them are no different than the chemicals you would buy at like the supermarket or like an auto parts store. Some of them are materials you won't see in those types of locations. So they're very tightly controlled, and safety, is our biggest and our number one priority at JSR, just as I'm sure you've heard it at other manufacturing organizations that use chemicals. But you have to have that kind of appreciation for the materials that we're working with, and to understand the hazards and the dangers, you have to have a little bit of a technical mind. And by that, I don't mean you have to have a degree or even like, a bunch of courses from high school that were specific for that. It's not like you need like AP chemistry or something to understand. It's just the mindset, right? To realize that even with all the systems on the software side and the devices that we construct and the containment that we put around the chemicals and double piping and all that kind of good stuff that we put in there to make sure the chemicals are safe. And just like the wafers, like the people don't touch the chemicals, right? We keep them separate, but the reality is there are chemicals throughout the plant. And so in order to engage with that safely, you have to have kind of that technical mind or curiosity, I would say. Beyond that, then, we also are looking for people that are good communicators, because again, the hazards on the job are real and the quality requirements for doing the process are very high. So if there's ever a problem with safety or with the quality, we want people to be really good communicators about that. People who just want to kind of clock in and go work off in the corner on their computer and then kind of clock out, that's fine. There's nothing wrong with those types of positions. But this isn't that type of position. So have to be really clear and communicative about what's going on. Is anything changing? Because like we talked about, the customer doesn't want things to change. Each batch should be the same. So a good degree of communication and a little bit of that social skill goes a long way as well. And then of course there are the physical aspects too. So we're filling like containers and drums, and so you have to be in decent physical shape. So nothing crazy. You don't have to pass like a physical fitness test or something, but it is maneuvering with these drums and these other materials at different sizes and masses. And so we have forklifts and we have walkie stackers and all that kind of stuff to help out for sure. But it's still, there is manual movement of these chemicals that's involved somewhere as well. So I would say those are the main areas that we look for in candidates.
And what does your typical day look like?
Typical day looks like for the manufacturing facility, it's pretty straightforward. So we have a plan of attack for every day, and that typically includes making batches or making different sequences of the product. So depending on whether you're on the raw material side, and so we have trucks that drive up and they have the chemical in them, and we have to hook them up to the factory and kind of offload the stuff from the truck. Or if you're inside the factory and you're working with the system to say, okay, we're going to make a batch of product A and we need to make 5,000 kilograms of it, kind of putting the recipe in there, making sure everything's been checked off and all the paperwork is correct, then monitoring the batch as it goes through, and then being a part of the filling sequence. So typical day is either being outside working with the raw materials as they come in and they're offloaded into the factory, or being inside, and that's in our clean room area. So you have to get suited up just like you see it like the semiconductor manufacturers. So you're in the bunny suit and everything and have like all the personal protective equipment on, and actually working with the material. So the tools and the machines, they do all the filling and doing all the process, but you have to monitor, make sure that we annotate everything that's going on, communicate with like other different teams, because saying, okay, this batch is done, batch 1 is done, let's start with batch number 2, and just getting all the batches moving through the factory, following procedure, making sure we're communicating if anything's going on, staying safe. So typical day is working with the raw materials or the finished goods as we make different batches throughout the day.
So the students have a really good questions. And so this one is, would you choose this career if you could make the decision again? If you could change, what would it be and what would you do differently? This is like
Wow.
like a Miss Universe.
Well, I would like world peace for no, I'm just kidding. But yeah, world peace would be good. I think the answer to that question is honestly, I would do it again. I think it's been a really good career. I know a lot of people that I went to college with and even high school have always had the question like, oh, but how long can semiconductor last, right? Like, I mean, you can do so much with like a smartphone now, like, how much more do we need? And the question has always been, there's always need for more, right? Amazon needs more for their, web services, and Facebook makes their own chips now. And so does Google and, Microsoft, they design their own chips now, and now AI is out there. So that create, so for me, I would, because it's been a good career, a long career, and it's still going. When a lot of people said, "Oh, that's small enough." Well, how small do you need a transistor to be? If I had to make another choice and do something different, and when I was in college getting the undergraduate degree, I was pre-med for a while, for a long time, and when I got into, my grades just weren't good enough for pre-med. I'll just leave it. I'll put it that way. But I would have loved to have gone into the medical profession if I could do it again, to go to med school and become like a surgeon. That would have been pretty awesome. But at the time, college was a big wake-up call for me, and everybody was smart, everybody was competitive. And so, yeah, I did pretty poorly my first year or two. And so that wrecked my GPA. Everybody's going to med school, they need like 4.0s or 5.0s or whatever the scale is, right? So at that time, then I said, oh, but there's this whole semiconductor side that's just as cool. And so never looked back.
And what degree of mathematical proficiency is necessary for your career? Like, do you really have to be really, really good at math?
No, not necessarily. Like I mentioned, like a technical acumen is really what's needed. And that doesn't mean like you could do calculus or something, or you can do, I don't know, like quantum physics or something, because I can't do that either. And honestly, why I went into chemistry and not chemical engineering is because I'm really not good at math. I mean, arithmetic, sure. And with the smartphones and the calculators, you don't really need it anymore, but what you need to do is like have that technical acumen. So even if I don't do engineering stuff, I can think about it and understand like, okay, what they're talking about, that makes sense, or it doesn't make sense. And I think the other part about being technical and needing what type of degree is not as important as it is critical thinking, which is also very important in our today's world with all the misinformation and that's going on in social media circles and stuff. Like, what do you know what's real anymore, right? And the key is to think critically, to say, wait a second, like, is this operation we're doing in the factory safe? Is this procedure right? Like, why kind of asking why, and not being the type that just takes a procedure and goes, all right, well, they gave me a piece of paper, they gave me like a printout or the procedure, and I'm just going to follow it, not ask questions. The part is to think about it kind of technically, like the technical parts about it, or like kind of the bare bones about it. Like, what are we actually trying to do, and not getting lost in the mumbo jumbo or the math and all that kind of stuff. And does it make sense? And if it doesn't, challenging it, because that's how people get better, and that's how companies get better, and our groups get better. So no, I wouldn't say that specific, like, basic math skills. Of course, that's going to be very helpful, because we need to understand, like, oh, does this weight look right? Well, is it in pounds or is it in kilograms? Well, can you multiply by 2.2 or divide by 2.2? Well, you don't have to get exact. You can just divide by 2 or multiply by 2. Stuff like that is what what we use. Everything else, you can do it through spreadsheets and calculators, and so that's totally fine.
The other ones are, what do you wish you knew but didn't when you first contemplated this career?
I guess I wish I knew how difficult it was to really do innovation. That would have been great, but I think everybody in this industry would have loved to know that too. I think everybody knows the difficulties that Samsungs or TSMCs or Intels are having these days, where they're trying to make the chips smaller, and they're trying to make things really smaller, and it's just difficult. It's not because they don't have smart people. It's not because they're not being clever. It's not because they're not working hard. They're doing all those things. And they're basically trying to do everything, throwing everything at it but the kitchen sink, that old phrase. They're trying everything. And it's so difficult, because when you get to this super small range, and you want to make chips, and you want to make trillions of them a day, and you want to make them the same and make them cheap, it's super tough, is really tough. So I wish I had known just how steep that difficulty curve would have known, but now we know.
So with what's happening right now, how have the recent supply chain disruption affected your day-to-day work, or just how had does the JSR Micro affected with the supply chain?
Oh, great questions. Yeah, you're right. These are excellent questions. So we're impacted by it every day. So the factory is new, but once we completed it, then our customer requirements are changing. So can you do this? Can you do this? And of course, we want to do that. And so we say, yeah, we can do this one, or we can't do this one, or we can do this one. The ones that we accept and we're still trying to do are impacted by the supply chain all the time. So construction projects are tough, because the materials are not easy. If you want to get steel, or you want to get high purity plastics, you have to get in line, right? And that includes like Intel down the street. They're in line too, and of course they're at the front of the line because they're bigger, and they're more massive in that sense. But even the raw materials coming in, so some of them, if they come in, by tanker, or they come by isotainer, they're run by truck drivers, right? So these guys and gals that are driving trucks, you guys have probably heard about the trucking shortage in the US too, right? So that's impacted us too, where we say, oh, we'll get that delivery of chemical X or something on Wednesday. Oh, it'll be actually like a week and a half later, because we can't find enough drivers, for example. So materials are hard to get. The drivers are hard to get to transport it to us. And then, the COVID itself, we've been able to work and build the factory through the pandemic, which I think has been like an outstanding success. But that has also diverted things too. Like, well, we'd like to get like this tank for, one of the gases or something. Well, COVID, they need, these metal tanks and stuff for hospitals, because patients need oxygen. And like, okay, that makes sense, but we have to wait now, because they're putting, kind of COVID related issues at the front of the line, understandably so. So that's an impact that we have to work through as well.
Hi. Okay. So before we keep going, because there's a few more questions, we will have the recording. We would upload it on YouTube by the end of today, for those of you who have to leave at 11. Brian, are you good to keep going and answer a couple more questions?
I'm good for a few more questions. No problem.
Okay. So let's see, where were we at? What are the most and least rewarding aspects of your job?
I would say the most rewarding aspect of the job are the people that we work with. And I know it sounds very cliched, but very motivated people, very smart people, determined, and to be in the semiconductor field, you have to be, right? You have to have a little bit extra because it's not just like, nothing against 3M or something, but it's not like making Post-its, right? Where that's kind of, they've done it, they finished it, they kind of understand. They're still making improvements, but it's not at the same pace or scale that semiconductor does or biotech does, right? For example, or alternative energy does. Like to get into those fields, you have to be really motivated, right? Because to stay and to catch up and, stay relevant, like you have to keep learning, right? And keep your mind open and keep talking with people. So, that's been the most rewarding part. The least rewarding, I would say probably like just the unknown, because it is one of, kind of like a basic science principle, like how long can they keep making transistors smaller and smaller? Is there a limit, right? So for the past few decades, the answer has been yes, they can keep making them smaller and smaller and smaller. There hasn't been like a limit in sight. But that I would say is kind of least rewarding, is that kind of unknown. But I think that's very germane to any industry, right? You never know when something's going to happen, even like a pandemic that nobody planned for. And then if you're in anything that's like a social service or, people service type of, or people oriented type of business, then very tough times, right? Where we've been fortunate and very lucky to still be prospering and growing, through the pandemic. So that unknown part, it can be a little bit unsettling at times.
Okay, and then one of our questions, it says, what are the best opportunities for someone entering a career? So any internships you can think of, or maybe classes they should take in high school?
Oh, sure. So I would say, yeah, any internship, I think, in something that has a little bit of, technicality to it, right? So that can be in biological fields or medical fields, that can be in any kind of engineering field. So that can range from petroleum to alternative energy. Semiconductor field would be nice, but electronics in general is always good. So something that has automotive is another great one, where they use tons of computer chips now and are facing like a computer chip shortage when we're talking about supply lines. So internships and anything that has some technical teeth to it, right? And so even if it's just like interning for like, like the dentist that's, down the block or something like that for a summer can be good, because I mean, yeah, there's medical elements involved with it too, but technical too, right? Like the tools they use, the procedures they use, how that they're analyzing, different patients' data and like the newest types of, materials or like, drugs or medicines that they use, right? These all have technical aspects to them, right? So I think that's always helpful because these are technical fields, right? So we talk about STEM fields, and that's the technical aspect is really helpful to get some piece of that under your belt. As far as high school classes, the traditional ones, like there aren't typically engineering courses in high school, but if you can get into like, any of the science fields, so earth science or geology, biology, molecular biology, chemistry, physics, right? And they're not easy. They're definitely not easy. So you have to work hard at it, but it engages a different part of the brain, right? It makes you work to understand like, how do these things behave? Why are all these laws here? Why do we have to learn all this stuff? And then the more challenging things like, okay, you've learned all the, especially in chemistry, you learned all these rules. Now we're going to throw different chemical structures at you on paper. Now see what you can do with them and what properties do they have. And so it really gets that critical thinking going and that structured thinking, which is really valuable in life in general, but also for like the semiconductor fields and for materials that we make at JSR.
Okay, and then it looks like our last question. How do you feel about the job outlook, the compensation, and the opportunities for growth in this profession? And what are they? I'm not sure what they mean by the last part.
Maybe actual price points, but without getting into the details, semiconductor is, again, a growing industry. Like it grows year over year over year, which is still amazing to me. So I think the career opportunities are still open and endless, but it is, again, a technical field, right? So you have to have a little bit of that technical acumen. And then as far as, the career growth, like it's pretty much, there aren't too many limits in that, because the manufacturing companies, from material companies like JSR to our customers to the raw material suppliers that we work with as well, they're all continue to grow. So that means opportunity, right? If the business or the industry was shrinking, then they want to cut costs, right? Then they want to cut people, and they want to do the layoffs or reductions and all that kind of, you know, horrible stuff that nobody really wants to experience or go through. But for a growing industry like semiconductor, you can grow, you can learn more, you can progress up different ladders, whether that you just want to, you know, kind of grow up a certain, you know, technical ladder, or, you know, engineering pathway, or even to management or into projects too. So it's an area that's ripe for growth and still expanding. Again, we built this factory like in the middle of a pandemic, which we didn't plan on it, of course, right? Nobody would, but we were able to pull it off and continue to do it because our customers are still demanding product, right? They still want more product. And so in order to do it, we had to, you know, make more space and make more capacity. And so that's just a snapshot of how the industry continues to grow in spite of a lot of swirl and turmoil in other industries and even on the geopolitical landscape, if you put it that way.
Yeah. Yeah, I learned a lot during this meeting. So, and a lot of questions, really great questions. So I think everybody's saying thank you. And I do want to thank you for having this presentation. Looks like a lot of people were actively participating. I'm going to go ahead and stop the presentation or stop the recording real quick.